Hello, welcome to this small lecture on time period of spring system. We have got a happy spring which is at rest when we suspend certain block of mass m and give little push or pull. This block will oscillate along with the spring with respect to mean position. This oscillation is nothing but actually simple harmonic oscillation. I can tell this as simple harmonic oscillation depending on two conditions. This satisfies two conditions. The first condition is the restoring force is directed towards a mean position, and the next condition is the restoring force is directly proportional to displacement. Anyway, the displacement is taken from the mean position in this direction, and same time the restoring force is towards the mean position. They are actually opposite. That's what we have as simple harmonic oscillator. So now this oscillating spring is considered as a simple harmonic oscillator. I wish to find out what is the time taken for each oscillation. So if this is a mass of pause, that block has got mass m, and from this position to and fro motion, what is the time taken for one full complete oscillation? That is what we have to find out. Now this says restoring force is directly proportional to displacement, and negative sign just tells that there is opposite direction. That's it. You can have a simple case as well. In a horizontal spring, place mass of the block is m, and here also the front and back motion. In this case also the same thing. It's a one-dimensional motion. Now this is replaced by a constant, that is k into x. This k is called as spring constant, which has a dimension of Newton per meter. It is just measure of how much stiff or how much soft the spring is. Now because of this restoring force, the block attached makes it move to the mean position in either sides, and that gives the acceleration of A. So this restoring force will give the acceleration of A, which is equal to minus k into x. And I told you this has a property of simple harmonic oscillation. And here the acceleration of the block, since it is simple harmonic oscillator, is actually minus omega square x. This is an expression extracted from a concept of simple harmonic oscillator, where omega is angular frequency, which is equal to 2 pi by t, where t is actually time period of this block because it's oscillating. Now this m into a is nothing but acceleration of the simple harmonic oscillator, nothing but the spring here, is equal to minus k into x, where k is actually spring constant, x is a displacement from the mean position. You lose your negative sign here, and I wish to have expression for omega first. Omega square is equal to x also you lose, and you'll get k by m. Negative sign cancel each other. So omega is equal to square root of k by m. I want to know what is expression for time period. So omega is equal to 2 pi by t, which is equal to square root of k by m, and this is t is equal to 2 pi into square root of m by k. Here is an expression for time period of oscillating spring. Time taken for each oscillation is just 2 pi into square root of m by k. Now comes a question on what factors this time period of simple spring system depend. And equation tells that t is directly proportional to square root of m. That means if you suspend more and more massive objects, time period is more. That means it takes more time to reach the mean position. More mass you suspend, more time it takes to reach the mean position. Also it tells that t is inversely proportional to square root of k. So k means the spring constant. I told you already, it measures how much stiff or how much soft the spring is. If spring constant is more, it means that the spring is more stiff. If spring is more stiff, k is more and t is less. That means if the spring is very stiff, the time taken for the spring to reach the mean position is very less. It makes its position in a very short interval of time. And if the spring is very soft, it takes more time to reach the mean position. If K is less, that means if the spring is soft. If this is less, this is more, that means time taken for one oscillation is more. And there is no dependence on G, that means it does not depend on gravitational acceleration. Whether you do experiment on Earth or Moon, or you go to the center of Earth and do the experiment, it is just independent. And also independent of the amplitude, how far you take this mark from the mean position. You make a long oscillation or a small oscillation, it does not matter as long as the Hooke's law values. The time period is also independent of amplitude of oscillation. That's all for today. Thank you for watching this.